Here's a project in Edmonton, Alberta. It's a duplex, so there are 2 units that you see there. They started with aggressive insulation package, high quality windows, mostly on the south side, did all the energy work, and then added the solar. And the vertical solar is solar thermal, which is principally for the winter, and then the angled solar are the PVs. So those generate the electricity for the duplex, and this is a net zero energy home. They tried to optimize it by looking at how much the cost of the energy efficiency was and related to the cost of the renewables, and find that sweet spot where it works out to be most economical. I'm not sure that they got it right, but it's a pretty good example. You can see over on the left where they started out in the 70s, and then the one in the middle shows that the 2000 energy standards that they now have in Canada. The dark blue is the heating load, so you can see on the far right here, or the near right, you can see the small amount of heating that's needed, and the pink is the hot water usage that they got it down to, and then the solar input is what's closest to me, and that matches it. So they're net zero. And it's basically looking at heat flows and trying to reduce energy use on all levels. They used double stud construction and filled it with cellulose, so they had R56 walls, R100 ceiling. And you can see here, I'll go through this fairly quickly. They used a drain water heat recovery to grab most of the heat that was going down the drain from when you take showers. And the combination of that and the solar domestic hot water eliminated almost all of their hot water needs. And you can see a comparison of a 70s house, a 90s house, and what they've done. They've got it down to what they call four slice toasters to heat the house, which is pretty amazing. Then they added the active solar water heater, the vertical portion, which got it up to a 96 energy guide rating. And then they added the PV to actually neutralize all their electrical needs. Problem is that, once again, it's pretty expensive. Now you take the solar electric out, and it's better. It's $40,000 to $60,000 extra. You take the solar thermal for space heat out, and that's going to knock 20 off of that. And it gets down to something that's fairly reasonable, and you can set things up so that you can always add the PV when it becomes more available, or more cost effective. And if nothing else, if you don't have all that money, you can just do whatever you can to make it ready to be net zero. So when we do a house, we always make sure that there's conduit between the basement and the attic so that we can get either water or electric lines between the two easily, in case we want to put PV on the roof at a later time. Now, this is the last thing I'm going to show you. This is the Bale building in Lapeer that we did. We just got through. That's a construction image right there. It's basically a classroom and a workshop for an environmental center that's part of a charter school in Lapeer. We used extensively renewable energy and green materials, and it's got a green roof on about a third of the roof. Here's the floor plan. And basically what we like to do is wrap the building in straw bale around 3 sides, and we actually change the shape of the building so we have a bigger southern exposure. And then add a large passive solar component to the south side. So we've got direct gain windows, we've got thermal mass walls, and a greenhouse, all supplying passive heat to the building. We've got sun tubes over the corridor and over the restrooms, so we don't need any lights on during the day. And we have a green roof over from here north is all green roof. This is them cutting the bales to size. This is something you don't see very often. the kids that are going to use the building are working on the building. They let them come out one day and throw mud at the wall. Basically, the straw bales are all covered with earth plaster, and then on the outside we did a final coat of lime plaster to give it a little bit more protection. And this is what it looked like at the end of their day. This is them actually mixing up the clay for the earth plaster. This is actually the lime plaster being run into the pump, and around the corner of the building they're spraying it out. So this was a building that was all contracted out, and then this is them troweling it out, and the finished product. They did a beautiful job on that straw. This is the entry. There's an earth roof over here. And we actually put enough structure, so we've got 6 to 8 inches of earth up there, so we're actually growing a native prairie on the roof. No sedum. It'll actually be what would have been there if the building wasn't there. And some of the stuff will grow this tall, so you can actually see it from the ground. And there's flowers and everything. A lot of people that were going to work on it suggested that we were making a big mistake because something else might grow up there that we didn't plan on. And it was like, I said, we're trying to create a native environment. And of course, yeah, we'll get some, and that's fine. But they wanted to control it all. It's basically an interior post and beam system with glue lambs. That's actually one of the truth windows, the sun on the wall. The center is actually a piece of plastic that covers up the straw, but you can see the straw, so you see that it's actually there. There's another truth window. We put all the electrical on the posts so that there's no electrical in the walls. Deep windows. Actually creates we used polished concrete on the floors. So this is the passive solar portion, and there's direct gain windows here, and these are mass walls. So this is mass. There's actually 8 inches of mass behind this glass. See that? So on the other side of this. And what that does is there's a 6-hour time lag between when the sun hits this wall on this side and when it comes out in the building. So you don't see any temperature rise on this until 3:30 or 4 o'clock at night. And it peaks out with a temperature of about 90 degrees at about 11 o'clock at night. So it puts heat into the building at night after the sun is gone. And by spreading it out, it's like making the day longer. It allows you to keep from overheating the building and get a larger solar percentage that way. There's another picture of the mass wall. The sun tubes. We put 400 square feet of solar thermal on the roof, which provides all the domestic hot water and provides some of the heat for the radiant floor backup system in the building. It's going to do about 20% of what's left over. And we've got 1,500 gallons worth of hot water storage so that we can store heat for several days for the building. This building was just completed, so I don't have any numbers to really show to you. There's 3 kilowatts of PV array on the roof. It's unisolar peel and stick, so this is on the roofing material before it goes up, and this is the roofers putting it on, and it's just the standard roof company putting it up. It's pretty neat. This is the north side of the building. 5 minutes, perfect. So that's where the green roof is, with 8 inches of soil, so we can grow everything that grows around here. All natives, nothing from out of town. And the greenhouse, there's a 8-inch mass wall here, so the heat that comes in through the greenhouse heats this wall up and heats the workshop that's on the other side of the greenhouse, other side of the wall. And that's the finished building. So we've got the PV array up here, built right into the roof, the solar thermal built right into the roof, the passive solar components, and the straw on the other 3 sides. And we do it because of them.